Section 11.4 is conditional probability. I can find conditional probability, and I can use tables and tree diagrams to determine conditional probability. Big ideas here for this section. A conditional probability is the probability that one event occurs given that another event has occurred. Conditional probability exists when two events are dependent. We write the conditional probability of event B given that event A occurs as P parenthesis B. We use this such that line that we've talked about before, depending on which notation we were using. When we used interval notation, we had to use that A, and we say the probability of event B given event A. So this line right here, we say given event A. A contingency table, or two-way frequency table, is a frequency table that contains data from two different categories, and we can use these and tree diagrams to find conditional probabilities. Example 1 is finding conditional probability. The table on page 696 shows students by gender and by type of school in 2005. We pick a student at random. What is the probability of the student being female given that the student is in grad school? So we need to look at the amount of females in grad school. So we look at the females in thousands and grad school and where they meet. And then we have to compare it to the total amount of students in grad school. So the total amount, we add them up. There's 1,349 males and 1,954 females. So when we combine those, (1954) over 3303, which is going to be 0.59, which is about 59%. So what this is saying is, based on this information, if we pick a student at random, there's a 59% that if they're in grad school, they're also a female. Now, using the same information, what is the probability that the student is female? So here, we're comparing females to all of the students. So, females, 2,462 in two-year colleges, 5,517 in four-year colleges, and again, 1954 in grad school, over all of them. So here, we take our males and our females. So our two-year colleges for both, our four-year colleges for both, and our grad schools for both. Again, it's female to all students. When we add these up here, we're going to get 9,933 for females out of 17,472 total students. And when we divide that, we're going to get approximately 0.569 or 56.9%. And that makes sense if we look at our data. There's more females in two-year colleges, in four-year colleges, and in grad schools, according to this information. I don't know if that's true nationwide or statewide or anything like that, but according to the information in this chart, so based off the people that they looked at, there were more females in every level, so there should be more than 50% females overall. So one quick way to check is to just look at your data and see, does my answer make sense? Now, what is the probability that a student is in a four-year college given that the student is male? So here we're looking for male students in four-year programs. So this one has to work for both conditions, provided the student is male. So now we're comparing all of the male students. So 1866 are in two-year, 4,324 in 4-year, and 1,349 are in grad school. Combine our denominator here to find the total amount of male students we have. 7539. So again, we want the total amount of male students to go in the bottom part. That's our A. Given that we're comparing all of the male students, how many of them are in a 4-year college? And when we divide here, we get about 0.574 or 57.4%. And that seems like it could make sense because if we look at our data, that's overwhelming the higher of the three. Example 2 is conditional probability in statistics. Americans recycle increasing amounts through municipal waste collection. The table on page 697 shows the collection data for 2007. What is the probability that a sample of recycled waste is paper? So we're looking for what is the probability that waste is paper given that it is recycled waste. Okay, which means we need to know the amount of paper that was recycled. So recycled and paper, 45.2 goes on top. So paper and recycled over the total amount of recycled waste. Total amount recycled. So we're going to take and add up 45.2 plus 7.2 plus 3.2 plus 2.1 plus 21.7. When we add all those up, we get 79.4. When we divide here to find our probability, we get about 0.57. 569, something like that, which is about 57%. So the probability that a sample of recycled waste is paper is more than 50%. And if we look at our data, if we look under a recycled column, paper is substantially higher than everything else. So it makes sense, okay? Makes sense that that could be our answer. Now, what's the probability that a sample of recycled waste is plastic? Okay, we take our probability that it is plastic given that it was recycled. Okay, plastic is more specific. It's recycled and it's plastic. That's what we're looking for. So out of all the things that were recycled, was it plastic? What's our probability? So here we have 2.1 for the plastic and recycled. Over, again, we said our total was 79.4. And we can re-add all that if we want. This is all recycled. But we figured it out in the last one, so we don't necessarily have to re-add it. When we divide here, we get approximately 0.02644, okay, which is 2.6%. So out of all recycled materials, about 2.6% is plastic. What is the probability that a sample of recycled waste is glass? So again, we want the probability that something is glass provided it was recycled. Probability of glass is 3.2, and all of our recycled is 79.4 still. So glass and recycled I'm going to start that over. Here we want glass and recycled, where they meet in our table, over all recycled. And here, 3.2 divided by 79.4 is approximately 0.0403, so about 4%. Take note here, conditional probability from page 697. For any two events A and B, as long as the probability of A is not 0, the probability of event B given probability A is going to be the probability of A and B divided by the probability of A. And again, probability of A can't be 0, we can't divide by 0. So a utility company asked 50 of its customers whether they pay their bills online or by mail. Using the information on the table on page 698, what is the probability that a customer pays the bill online given that the customer is male? Okay, so we're going to do probability of online given that he's male. So we need the probability of A and B over a probability of A. Here, that's going to be the probability of male and online divided by the probability he's male. If we look at our chart, the probability of male and online is going to be 12 out of the total number of people. So we need to add up all of these values to see how many people there were overall. We have 12 and 8 male and 24 and 6 female, which gives us 50 total people. And that's what we divide by. 12 out of 50 people are male and order online. And of those, 20 are male out of 50. When we divide our fractions here, we end up multiplying by the reciprocal. Top goes to bottom, bottom goes to top. Simplify what we can. I can also take a 4 out of these. Gives me 3/5 or 0.6 or 60%. So according to this, the probability that a customer pays the bill online, given that the customer is male, so out of the males, about 60% of them pay online. So provided that we're talking about just the men here out of this experiment, 3 out of 5 or 0.6 or 60% of them pay online. Now, researchers asked shampoo users whether they apply shampoo directly to the head or indirectly using a hand. What's the probability that a respondent applies shampoo directly on the head, given that the respondent is female? So we want the probability of directly on head, directly and female, over the probability that a person is female in this scenario. So if directly and female is going to be 6 out of the total number of people. And again, 2 plus 18 plus 6 plus 24. Males, females. Gives us 50 again. Over the probability of female. The probability of female is 30 over 50. So 6 over 50 times, multiply by our reciprocal, 50 over 30. Simplify what we can. 1/5 or 0.2 or 20%. Again, 6 directly on head, 30 females, 50